Hi, I'm Christian, and I'm excited to be introducing the topic of visual tools for cyber analysis. Before I get started, I'd like to thank the conference organizers. Organizing an online conference has its own challenges, but I'm grateful to be in the company of some great speakers and sessions. You probably know that this is being pre-recorded, so I should hopefully be in the chat today to answer any questions as we go along, and I'll also be posting some links to some of the content as you see it. When used with care, data visualization is an extremely powerful method of communication. It allows us to take complex data and complicated scenarios and make them easier to understand. A good data visualization will illuminate, inspire, and inform. My data visualization specialty is that of network graphs and visual network analytics. This is a particularly interesting approach to data visualization as it helps us understand a world full of connections. Networks are all around us. Transactions, communications, family trees, social networks, circuits, maps. Everywhere you look, you'll see networks. Unfortunately, the first result when building your own visualization of a network is often something that looks a little bit like this. This is sometimes referred to as a hairball, and it doesn't tell us much about the underlying data. The only things I can really determine is that everything is pretty much connected to everything else. There's a wide range of colors used, that probably means something, but unfortunately the grey links are occluding the nodes, which makes it worse to see what's going on. Here's a slightly better example. This is one I made showing the links found in popular newsletters in the last half of 2020. We can see some structure in this network. For example, some of the large clusters of pink nodes are where certain newsletters have linked to one article that no one else has linked to. So why are these visuals so common? I see them in blog posts, marketing materials, and magazine covers. One answer is that they're just cool. Using gradients and fancy color schemes and animations is a surefire way to turn heads and get attention. It can be a way to get people interested in your product and to attempt to show that you have a strong understanding of a domain. The other answer for why these hairballs are so common is that it's simple to create something complex. Today I'm going to walk you through how we can move on from trying to impress people with pretty pictures to actually leveraging them to fight cyber threats across a number of use cases. In particular, I'll be advocating for the use of interactive network graphs tailored for use by specialists with a specific goal in mind. Here's a quick breakdown of the talk. I'll give a summary of what I mean by visual analytics. I'll walk through the challenges of it in a cyber context, before finishing with some examples of their use with some pitfalls and tips along the way. It's a wide topic, so I just want to whet your appetite today. You can find sources and links on my site, the URL in the bottom left-hand side of this slide. I focus on visual network analysis, which is the use of visual representations of graphs augmented with other data to detect and understand cyber threats. Visualizations like this can sometimes be considered to be a bit of a distraction. They sometimes get a bad rap. I said it's simple to create something complex. It's hard to go to that next step and make network graphs robust and useful in a reproducible way. The important part of this definition is connected data. But before I give more examples of what this can be, I want to take you back to 2005. Perhaps a few of you in the audience are familiar with the 2005 Death Cab for Cutie album Plants, and one of the hits, there are different names for the same thing. Network graphs are a bit like that. People use many different ways to refer to them. In the field, I've heard all these words to describe graphs. Networks, maps, charts, spiderwebs. Which of these is correct? Well, when it comes to network visualization, I'd say they're all fine. Some may argue with me on the subtle differences between them, but for our purposes today, all that matters is that we're working with data that's connected in some way. While I'm at it, I'd like to clarify a couple of confusions in the space as well. The less catchy 2021 graph B-side for the Death Cab song could be same names for different things. The word graph and related topics are a touch overloaded. Take Graphql. There was a talk on this yesterday. Confusingly, Graphql isn't a query language for graphs, nor is it a graph database itself. Graphql is a query language to build APIs with its own ecosystem of API tooling. It has graph in the name due to the nested nature of the queries. The other confusion is knowledge graphs. It's hard to pin down an exact definition of what a knowledge graph is. The situation was muddied somewhat by Google referring to their algorithm for organizing all human data as a de facto knowledge graph. That's what you can see on the right hand side here. This is an info box for when you search for something on Google. In this case, I'm actually surfacing the knowledge graph itself as the knowledge graph. Confusing, eh? Many people call what I'm showing today knowledge graphs, but some people would argue that's not strictly true. But for us today, we don't really care about that. We just care about showing where entities are connected. There isn't much more to it than that. So at a fundamental level, this is what we mean by connected data. Here we can just about see 3 nodes connected via 2 links. Some people call nodes entities or vertices, it doesn't really matter. And in our domain, these are likely to be hosts, devices, users, or processes. Links can also be called connections or relationships, or edges. And these could be, say, access log entries, communications, or even transactions. Once these connections are surfaced in a dataset, we get a bigger picture that can be a little bit more useful. This is an example of a source code repository analysis. It's actually a tree of a file system where larger nodes correspond to files with more lines of code. There are many different ways to organize and visualize graphs. I'll be mostly focusing on force-directed graphs today, but it's worth knowing that there are other methods at our disposal with their own benefits and downsides. On the bottom left, we sometimes refer to this as a chord diagram, and it's good for showing pairwise and categorical comparisons. Meanwhile, on the bottom right, we have a matrix, where each cell is colored if there's a connection between the row and the column. These are arguably more readable than network graphs, and commonly used in source code analysis and reverse engineering. All the graphs on this page are a reasonable size for surfacing for end users in a visual environment. A common method is to restrict the size of our network based on some sort of boundary, so that we can show off the size and category of the information without overwhelming and to aid the analysis of a network itself. I've alluded to a number of challenges in this space. I'd like to summarize 7 of these today. These challenges are faced by threat intelligence and SOC analysts, pen testers, and security administrators looking to understand and defend against cyber threats. They're also common if you're doing a quick, one-off analysis project with your programming language of choice. The first 4 challenges could be grouped into a bucket of data problems. You can remember them with VVQ, LOL. Just kidding, I just thought that was funny. To start, we have the 2 V's of big data challenges. We've been told for years that data is big nowadays. I'm sure many of you in the audience work with large datasets on a daily basis. And it's tough. Most tools will attempt to aggregate or summarize, and it's hard for analysts to trust that important data facets haven't been polished out to create a simple representation. Also, as data volumes get larger, it's anticipated that interaction feedback gets more latency. This is important if we're aiming to use tools that aid people's flow rather than getting in the way. The next V is variety. We could be pulling data from various sources with their own data dictionary and storage. How do you pick the sources that are most important? The promise of SIMS is to assist with this, but that's still an unsolved problem. Quality. Whether it's log size limits truncating data, invalid data, or corrupted in transit, data quality is an eternal challenge. Garbage in, garbage out. It's common to have bias towards more recent data sources, which makes it ironic that big historical data doesn't necessarily imply big confidence. Finally, LOL is lack of links. With network analysis, we're always looking for connections to tie data sources together. Keys can be difficult, but there's a trick I'll come back to later when discussing real sources. Visual analytics solutions are often described as having AI or artificial intelligence. And to be cynical for a second, it's often difficult to see through the hype and the marketing. That's not to say there isn't fantastic AI research being done. It's just that it gets diluted by the time it gets to industry, usually because analysts reject algorithms telling them that something is suspicious by some opaque logic. Cadence is the challenge of providing a tool to augment an analyst's understanding of a typical problem and threat in the network, and our tools should help us identify user and system processes and aid this understanding, not distract from it. I like to call this AI augmented intelligence, not artificial. Threat triage is the cycle of detect, investigate, resolve. But taking a visual approach to this is fraught with pitfalls around collaboration, creation of deliverables, or consumable products. The final challenge is that of risk and reward. We weigh up the cost of bringing additional data points into our visualization to aid with the analysis, but with the potential benefit of the additional context. Explore versus exploit. This isn't always easy. So there we have the challenges. It's a lot. Unfortunately, there's no free lunch. Visual network analysis will assist, but it's far from a silver bullet. Nevertheless, let's look at the tools available that help us hit these challenges head on. It's hard to draw up a summary of the space, as you could argue on the inclusion of databases, programming libraries, vendor platforms. I've given it a go anyway and tried to plot things out on an axis. We have DIY from the bottom to the top, to platforms, and then from left to right we have permissive over to proprietary. Now in the bottom left we mostly have languages and libraries to build applications from scratch or work on a small scale problem. Gephi is a very popular open source GUI application that allows you to build networks from scratch, whereas D3 is quite a low level JavaScript library for the browser. On the bottom right we have more commercial projects, and there are a number of toolkit vendors in this space if you're not looking to use open source. I actually worked for one of them, Cambridge Intelligence, and I help developers build interactive, browser-based visual network analysis applications in JavaScript. A little bit above that, the solution vendors box is also a little vague. I actually work with a number of vendors, so I didn't want to call out any in particular, but I made an exception for some companies offering interesting platforms. Finally, on the right, I have two thick client applications, Maltego and Analyst Notebook. These are desktop applications with wide use across the industry and elsewhere. There's a clear split between thick client applications that need to be installed and run on a server or a computer versus browser-based applications, and suffice to say, the browser is much more forward-thinking at this point. When building scalable visual network analysis applications, graph databases are databases that are well suited to inherently connected data. A lot of people assume this means that a graph database is the only thing that can be used to store graphs. This isn't true. A purposely indexed Postgres database is a perfectly reasonable backend, one which you likely already know how to query. But if you're starting a greenfield project with connected data, you could consider using a graph database. Just to highlight a few on this slide, at the top we have Neo4j. Neo4j is by far the most popular graph database and has a really good learning curve for new developers. OrangoDB is a good alternative. It's a multi-model database, so a graph model is just one piece of what it offers. It also has a document store and a key value store. And over on the far right, we have Azure Cosmos and AWS Neptune. These are hosted solutions that may appeal if you're in those environments. For each of these cyber applications, I'll be answering three key questions. What is it? What's the risk? And how can visual analytics help? You'll see that the three examples do overlap. This isn't a prescriptive thing. Techniques used in each can help with the others. So to start things off, I'm going to look at dependency analysis. Software and processes often have a vast tree of dependencies, often abstracted away into a directory or package management. Take React, the popular front-end framework. It has a popular bootstrapping tool, Create React App, and here's a dependency tree of all the packages pulled in when you first initialize a project. This was drawn with an application called Graphql, or a library called Graphql. It's actually been around for over 30 years, which is fantastic, and it does a really good job at laying out complex trees like this. The downside of this library is that it creates very static visuals. It's not really very modern in terms of how I could interact with it in the browser. The power of visual network analysis is enabled through interaction with the browser, so I would want to be doing some sort of zooming or selection in order to highlight more information on this network. So here's an example of this in action. I'm able to zoom in and look at something in more detail, and by clicking on a link or a node, I can see the direct neighbors of it for more information, which is really nice. To take this one step further, here's an example application from academia. I think this is a really amazing way that you could interact with a tree like this. And you'll see here that I can pan around and I can select nodes and I can bring the neighbors to me instead of forcing my user to drag around the network and explore it on their own. If you see here, we'll also select some nodes and we're able to select the neighbor and then it will fly over to where that neighbor is in the tree. So you have this sort of mental model of the network that you can explore and understand where you are at any time. So now when I click free, I'm taken over to there and I can sort of traverse the network on demand. I'd love to see this in a modern cyber analysis tool, and it gives you a glimpse of the sort of functionality that could be included in the future. Going perhaps a little too far, there's a lot of interest in the use of 3D with large graph datasets. This is a brilliant browser app where one can fly through a galaxy of dependencies in the Node Package Manager ecosystem. It's quite hard to imagine this actually being useful in a cyber context, but perhaps with the rising popularity of VR and headsets, it could be the cyber defense app of the future. Oh, and here's an obligatory GIF of Minority Report. You can't mention futuristic user interfaces without name-checking this movie. The next use case I'll look at is asset relationship maps. Visio is the de facto tool for building network diagrams manually. That's what's used on the left. The right is a modern alternative that's a web app. The problem with this approach is that by the time you've drawn your intricate map of connections, it's likely to be already out of date. It's also not reasonable to expect a DevOps engineer to draw hundreds, thousands, or more devices manually. And with the popularity of virtualization and orchestration technology like Kubernetes, the complexity of these environments has ballooned. These maps are important for threat model assessments, and overlaying multivariate details like access rights can provide critical context on attack paths that could be leveraged. Here's an example of a dynamically generated network of assets connected from somebody's dorm room at school. Now this is starting to look a little bit like a hairball again, but using the interactivity techniques I highlighted on the last section, we can explore and understand this map in more detail and maybe find something of a vulnerability. We often rely on layout algorithms to do a good job at laying things out on the screen. Here's an example of one that's been run for a small network. Here we take advantage of physics simulations to pick apart complicated networks and display them in an appealing and insightful way. These physics simulations pretend that the links between nodes are actually springs, while the nodes themselves are weights. After initializations, these will hopefully settle down. Now you are able to typically tune these parameters for these physics simulations, and here's an example of me doing it live. So now I'm actually tweaking the charge or momentum of the initialization, resulting in a continuously updating graph. Of course, you'd never put this in front of an end user. It's a pretty extreme example, but it isn't unusual to see overly active graphs. These are confusing, distracting, and above all, unhelpful. There's nothing wrong with an interactive but static graph. Just because you're using physics doesn't mean you have to show it. For our asset relationship maps, the use of hierarchical layouts can highlight the flow of data and information through a network. The final use case I want to introduce today is that of user entity behavior analysis. This is where we blend access logs with other data to understand user behaviors and spot anomalous activity. Taking a network of hosts, users, devices, and with the intent of understanding risks, I like to think of this at 3 different levels. Firstly, we have entity level concerns. This is that some property of the entity or user that's anomalous in itself. Maybe it's an alert of a device with some sort of uptime or similar. Typically, these are facts that we're interested in knowing if they just exist at all on the entity level or on the node level. Next, we have connections. These can be the steps users take or data transfers that take place. We take one step out of the network and look at the links themselves. It's common to use threat intelligence sources like malicious IP logins from a surprise country, and these are things that could flag at the connections level of the UEBA. Now remember the challenge of lack of links? Sometimes we find that keys aren't possible to be matched against when we're using IP addresses or other similar data sources. It can be hard to have these common keys to link disparate data sources. Now one approach you could take is to use the trick that everything really has a timestamp. So there's nothing stopping you from overlaying quite disparate data sources using the same time series analysis. So here's an example of a window of time and a timeline at the bottom, along with a topological graph view of a dataset at the top. Using this, one could spot and drill down into activities that look suspicious, and using things like tooltips, we can get details on demand of facets that we want to look at in more detail. In UEBA, we use machine learning models of normal activity to build and serve as a behavioral baseline. In our visual network analysis, we can take this one step further, and we can look at this at the network level, namely by monitoring network velocity. This means looking at how quickly connections are built up over time. There's a rich field of graph and network analysis that underpins our work in this space, and I'd like to finish up today by describing one small piece. I know it probably seems like years ago, but do you remember when that big boat blocked the Suez Canal? Here you can see other container ships making a long trek around the Horn of Africa due to the blockage. One way to think of this is that it's a massive graph problem. We have ships around the world looking to find the shortest path between 2 points, and invariably this results in the use of the Suez Canal. In the graph world, we could say that the canal has a very high betweenness centrality. This is just a fancy way of saying we look at the structure of a network to determine nodes of particular importance. Now in a dependency tree, asset map, or in UEBA, this can be helpful to identify entities that could be the target for an attack. So that's it for today. I've covered 3 applications of visual analytics in a cyber context and give a flavor of the problems and solutions in this space. If you enjoyed this talk today, I have a newsletter on graph visualization and related topics called Source Target. You can sign up at sourcetarget.email, and here's my contact details otherwise. I'm happy to take any questions now, and I'll see you around on the chat.